Hey Science 10, welcome to physics. This is going to be our first lesson. We're just going to learn about motion today. So let's take a look at a simple definition. So motion is the change in an object's position relative to a reference point. So a reference point is any point really where you start to take a look at it to see if there's any motion. So in this case, we're going to call that point 0, and then we're going to take a look that there was movement. Here's another example. If you compare A to B, you'll see that here's a reference point, doesn't change. However, the amount of motion changes. We call this distance. So uniform motion is the simplest type of motion. It describes an object that is traveling at a constant speed in one direction. That's what's important. It's a constant speed and in one direction. Constant means non-changing. The speed does not change. This type of motion is nearly impossible on Earth because various forces act to slow down objects such as friction. And even if you have cruise control on your vehicle, even the road conditions are going to mess up this constant speed. So it's more of a theory than a real life experience. Because uniform motion is difficult to maintain, we take a look at the average speed. Okay, that's what we're going to be looking at when we're talking about uniform motion. So what is average speed? In this case here, or in any case, we're looking at two things. We're looking at distance and we're looking at time. The car moved a distance of 5 meters in a time of 1.2 seconds. It did not exhibit uniform motion because it sped up and slowed down. However, the average speed of the car is defined as a change in distance, that's important, during a certain time. Very important. That is what average speed is. We're just looking at two variables, distance and time. So there's the formula for average speed is equal to delta D over delta T. Delta is a Greek letter and it just means change in. So your V, your average speed, V means speed, okay, is measured in meters per second. Your change in distance is measured in meters, and it's basically taking a look at the distance traveled. And your delta T is your time lapse, or your change in time, and it's measured in seconds. These units, kiddos, are very important. Speed is meters per second because distance is measured in meters, and time is measured in seconds. So here's an example I'll walk you through. A person walks 10 meters away from a stop sign in 5 seconds. What is the average speed of the person? Okay, so let's take a look at our formula. Average speed is equal to distance traveled over time lapsed. V is equal to delta D over delta T. But we're going to articulate further what this change in distance and change in time actually means. Basically, change in distance means you're looking at the final distance subtract initial distance, and your change in time is your final time subtract your initial time. But in our question, it just tells you the distance is 10 meters and the time is 5 seconds. We make the assumption that if 10 meters were traveled, the object or the person started at 0. And if 5 seconds was the time, we have to make the assumption that it started at a time of 0 seconds. But just so you have the background, so here we have 10 subtract 0 and 5 subtract 0. So really it's 10 meters over 5 seconds, divide the two, and you get your average speed of 2.00 meters per second. All right, now let's take a look at another example. A huge ocean wave or tsunami travels a distance. So here we have our distance of 4.06 times 10 to the power of 6 meters. And we have our time, 3.4 times 10 to the power of 4 seconds. What is the average speed? So first thing I want you guys to do is list all your knowns and unknown variables. That's step number 1. So let's go ahead and do that. So we know that we have our distance is equal to 4.06 times 10 to the power of 6 meters. And we know that our time is equal to 3.4 times 10 to the power of 4 seconds. And we know that we are looking for the speed. I'm actually identifying what I'm looking for. That way we're not confused. Step number 2 is write the formula. And just plug in data. Okay, let's go ahead and do that. V is equal to distance over time. V is equal to 4.06 times 10 to the power of 6 meters over our time, which is 3.4 times 10 to the power of 4 seconds. We use our calculators to figure this out, and we should get an answer of 119.4 meters per second. So let's just take a look at this number here. If we wanted to round it off to 3-digit whole number, we would have to take a look at this and say, okay, it's not higher than 5, so my answer could be 119 meters per second. That is my distance. Okay, let's move on to another example. A Concorde airplane could fly at an average speed, so let's unpack our question, average speed of 694 meters per second. Calculate how long it would have taken the Concorde to fly around the world, which is approximately 4.00 times 10 to the power of 7 meters. So let's go ahead and write all our variables, right? So we have speed, distance, time. What do we know? We know our speed, 694 meters per second. We know our distance, 4.00 times 10 to the power of 7 meters. And we're looking for our time, and that's going to be in seconds. All right, so then we write our formula. V is equal to distance over time. We're not looking for V, we're actually looking for time. So let's go ahead and manipulate the formula. Remember step number 1, or step number 1 is to make it linear. I'm going to get rid of this t in the denominator and bring it up to the numerator. So I'm going to multiply this by our t. This cancels them out. What I do to one side, I do to the other. So I'm going to multiply that by t. So now I have distance is equal to time times volume, but I'm not looking for distance, I'm looking for time. So now once my formula is linear, I can now isolate. I can say, okay, I want t by itself. So t is equal to d over v. Make sense, kiddos? Because I want to isolate this. I want to divide this by v. I want to divide this by v so that this cancels out. So I have a formula. T is equal to distance over volume. My distance is 4.0 times 10 to the power of 7 meters over my speed, which is 694 meters per second. My meters cancel out, as you can see. My time then is going to be, once I calculate it all out, 5.76 times 10 to the power of 4 seconds. Okay. Awesome. Let's move on to a different question. An electric train is traveling at an average speed. So again, we have average speed 6.9 meters per second for 4 seconds. Now we're looking for how far? We're looking for distance, right? So we have v is equal to distance over time. For speed, we have 6.9 meters per second. Our distance we're looking for, and our time is 4.0 seconds. All right, let us use our formula. V is equal to distance over time. We're not looking for speed, we're looking for distance, right? Speed is equal to distance over time. So now I'm going to isolate, or I'm going to make it linear, I should say, and then I can isolate. So distance is equal to time times speed. Okay, we're looking for distance, so it works out. So now I just have to plug in my numbers. Time is 4.0 seconds times my speed, 6.9 meters per second. My distance is going to be 28 meters. Awesome. So those are just 3 examples of the 3 different things you could use, or you could find using your v is equal to distance over time. So let's take a look at using graphs to analyze average speed. So for uniform motion, two types of graphs can be used, and you have to know the difference between the two, kiddos. We have our distance versus time graph, and then we have our speed versus time graph. Our distance versus time graph is just looking at distance and time, and our speed is actually, right, meters per second, and our time is in seconds, whereas distance over time is just meters and seconds. So these graphs provide a visual representation of motion. So let's take a look. A motorboat is traveling at a constant speed. A person on the shore is recording the distance the boat travels away from the first marker buoy every 2 seconds. So here's our information and here's our graph. So at a time of 0 seconds, the movement is 0. Okay, so it's plotted here. After 2 seconds, we have a movement, or it had traveled 10. So there's our data point there. At 4 seconds, it traveled 20 meters. So here's at 4 seconds, it traveled 20 meters. At 6 seconds, 30. At 8 seconds, 40. And at 10 seconds, 50 meters. So when we take a look over here, for our distance versus time graph, we know that this type of slope is showing us uniform motion. Now, it doesn't have to be smack dab in the middle. It could be here, it could be there. There's still uniform motion because of the shape of the slope. However, this just kind of talks a little bit about how fast some things are going, okay? So basically, take a look at the shape of the slope on the distance time graph. So how do we find the slope on any point? It's rise over run. And what that means for rise is this change in y over change in x, right? And your y is your change in distance, and your x variable, right? This is your x, and this is your y. So and that equates to average speed of the change in distance over change in time, your delta d over your delta t. The slope of a line on a distance time graph, so the slope of this line, is actually your average speed of the object. So here's an example. This is where you find your rise and your run. So your rise is this right here, and your run is this over here. Okay? So here's an example walking you through it. Starting at 0, so we're looking at the slope of this section here. I always like to start it at 0, it just makes life a lot easier. If you take a look at your rise over your run, your rise is 30 meters and your run is 6 seconds. You divide the 30 divided by 6 and you get an average speed of 5 meters per second. So the slope of a distance time graph is a visual representation of the speed of an object. A steeper slope indicates a faster speed and a lesser slope indicates a slower speed. So let's take a look at what that looks like. Here's our distance time graph. If we take a look at, if we take a look at the different cars, all three cars have constant speed because the slope of their line does not change. So if you take a look at car number 1, it's traveling at a constant speed, but it's going faster. If I'm comparing 1 to 2, it's going faster than car number 2 because it's a steeper slope of the line. Car 2 is traveling at a constant speed, slower than car 1, right? And if you take a look at car number 3, it's actually stopped. What that means, let's just pretend this is 5 meters. At 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, it stays at 5 meters. It doesn't move. It's stopped. So for a distance time graph, a straight line anywhere on the graph is going to show that the object is at rest, or the slope is 0. So let's compare a distance time graph to a speed time graph. So the time doesn't change, it's in seconds. However, now instead of distance, we're looking at speed. 5 meters per second, 5 meters per second, 5 meters per second, 5 meters per second. So now, if we take a look at the slope of the line, if it's a speed versus time, uniform motion is showed by a straight line. Whereas distance versus time, it was that kind of line, and it could have been any of these are examples of uniform motion. For speed versus time, a straight line shows uniform motion. At 0, at 2 meters, at 2 seconds, 4 seconds, 6 seconds, the object is traveling 5 meters per second. Okay, a horizontal line has a slope of 0, and that means that the speed stays the constant as time passes. So a slope of 0 for a or a horizontal line on a speed versus time graph, it's uniform motion. Yay, uniform motion. So here's an example of more of a real life situation. You have a time at 0, 5.8 seconds, 1, 6 seconds. Take a look at the fact that it's not exactly perfect. So once I plot these numbers in, what I need to do is I need to put in a line of best fit. That is a true representation of the average speed. So it's still uniform motion because it's looking at average speed, kiddos. It's not exactly, this is more real life. There's no way that something is going to travel exactly 6 meters per second for every second. So we put a line of best fit to show that it's average speed. So the slope of a line of a speed time graph indicates that an object is either speeding up or slowing down. So in this case here, when we're talking about speed versus time, this is uniform motion, right? And it could be anywhere on the graph except one place, and I'll show you that in a minute. But if it's moving up, it means that the object is increasing in speed, it's accelerating. If it's actually pointing down, object is decreasing its speed, it's negative slope, or it's decelerating. If you have this right on the 0, that means the object is at rest. In other words, it's not moving. Because it's traveling 0 meters per second for every second. It's not moving. That's what happens when this is what your car does at a stop sign. So the area under a line of a speed time graph determines the distance the object travels. So what the heck that means is that if I take the area of the speed time graph, we can actually find the distance that the object traveled. A boat is traveling at a rate of 10 meters per second for 5 seconds. So here we have 10 meters per second, and it traveled that for 5 seconds. If I take the area of that, it's going to give me a distance of 50 meters. So this area here is actually equal to your speed times time, and it's going to give you your distance. So it's like manipulating your formula, okay? So here's some practice. The data collected in the table is for an object traveling at uniform speed. Draw a speed time graph for the data. Then what is the slope of the line? Why does the slope indicate uniform motion? And what is the area under the line for the time interval of 0 to 5 seconds? And what does the area represent? Okay, let's take a look. So first of all, let's plot. So speed versus time, we always need a title. We always need to make sure that the x and the y axes are labeled. So at 0, the speed is about 9.8, so about there. And at 1, it's 10, so that's probably 1. At 2 seconds, it's 10.2. Let's go there. At 3 seconds, it's 10. Oh, where's my 3 seconds? About there. At 4 seconds is 9.9. Maybe there. And at 5 seconds, it's 10.1. So it's not exactly perfect, but you're still going to put in your line of best fit. Okay? So that is still showing uniform motion because it's speed. So what is the slope of the line? It's a horizontal line. Why does the slope indicate uniform motion? Because an average speed is 10 meters per second, right? Because it's about 10 meters per second after 1 second, 2 seconds, 3 seconds, 4 seconds. It's probably you can probably extrapolate it longer. what is the area under the line? Let's take a look from 0 to 5, right? We want to find this area here. So v is equal to distance over time. We're going to manipulate this to find distance. So we're going to get rid of our t. Oops, I put it in the wrong spot. Times that by t. These cancel out. Distance is equal to speed times time. So at a distance here, at 5 seconds, so we can say distance is equal to 5 seconds times 10.1 meters per second. So we kind of can say, right, at around, after 5 seconds, it traveled 50 meters. And it's as simple as that, kiddos. And the area here represents the distance. And that's it. Have a great day, and I will see you next time.